Okay, good afternoon, good morning, good evening, good night, depending on when you're watching this video. In this video, we're going to work through an example of how to compute the sample mean and the sample standard deviation by hand using the data of girth of black cherry trees given on slide 41 of lecture set 2. All right, so in this example, I will provide a complete breakdown of how we can compute each of those two quantities, the sample mean and the sample standard deviation. I will be using the summary notation that was introduced a few slides back. I will also compute the sample standard deviation in two different ways. You do not have to do this on an assignment or a test. You only have to compute it in one way, but for illustrative purposes, I will show you both ways of getting that value. All right, so the first thing I'm going to do is focus on the sample mean. Okay, so as a reminder, the sample mean is given by x bar is equal to the sum from I equals 1 to n of xi divided by little n. Right? So in this situation, little n is going to be equal to 6 because we have 6 observations in the data set, right? And now what I'm going to do is I'm going to designate each observation with a x notation. So we have x1 is 8.3, x2 is 10.5, x3 is 11.1, x4 is 12.9, x5 is 13.8, x6 is 14.5, right? Okay, my sample mean, so x bar is equal to the sum from I equals 1 to n of xi over little n. So this is telling me x1 plus x2 plus x3 plus x4 plus x5 plus x6 divided by little n. Right? So again, that's what that summation symbol means. It just means add up all the values between I equals 1 and n. And then again, for clarification here, this little n on the top, this is actually equal to 6, right? It's because we have 6 observations. So we're adding x1 to x6 together, and then we're dividing by little n. Okay, so this is simply going to be 8.3 plus 10.5 plus 11.1 plus 12.9 plus 13.8 plus 14.5. And that's going to be divided by 6, right? And that will give us a total of 71.1 divided by 6, which is equal to 11.85. Okay, and that's our sample mean. All right, now for the sample standard deviation, we can proceed in two ways. We can use either the defining formula or we can use the computing formula. So if we use the defining formula, and just for clarity, this is going to be the sample standard deviation. Okay, so our defining formula is equal to little s, which is equal to the square root of the sum from I equals 1 to n of xi minus x bar squared divided by n minus 1. So this is the first way that we can compute the sample standard deviation. Now, the easiest way to do this is to use a table of the squared differences. Okay, so in our table of squared differences, we will have our observations. So 8.3, 10.5, 11.1, 12.9, 13.8, and 14.5. Right, so these are each of the xi values in our data set. Right, and then in the second column, we're going to take each xi value and subtract the sample mean. So for example, in the first column, we will have 8.3 minus 11.85. In the second column, we'll have 10.5 minus 11.85. In the third column, we'll have 11.1 minus 11.85. In the fourth row, not column, in the fourth row, we have 12.9 minus 11.85. In the fifth row, we have 13.8 minus 11.85. And in the last row, we have 14.5 minus 11.85. Okay, so this will give us the difference between each observation and the mean, which results in negative 3.55, negative 1.35, negative 0.75, 1.05, 1.95, and 2.65. Okay, and then in our third column, we're simply going to take each of those differences that we just computed and square them. So for example, in the first column, we have negative 3.55 squared. In the second column, we have negative 1.35 squared. In the next column, we have in the next row, we have negative 0.75 squared. Then we have 1.05 squared. Then we have 1.95 squared. And then we have 2.65 squared. Okay. All right, so this gives us the following: 12.065, 1.8225, 0.5625, 1.1025, 3.8025, and 7.0225. Okay, so this is our table of square differences. Now, all we have to do is take what we have calculated here and plug them back into our formula for sample standard deviation. So we have S is equal to the following. So this is going to be the square root of the following. So we will have x1 minus x bar squared plus x2 minus x bar squared plus x3 minus x bar squared plus x4 minus x bar squared plus x5 minus x bar squared plus x6 minus x bar squared. Okay, and then this whole thing will be divided by 6 minus 1. Okay, and the square root is meant to go over everything inside here. right? And again, the little n here is a 6. So we have 6 observations. So what is this going to give us? Okay, so I'll put the square root sign on after. So from our table above, we have 12.065 plus 1.8225 plus 0.5625 plus 1.1025 plus 3.8025 plus 7.0225. This whole thing is divided by 5. Right? So that will give us the square root of 26.915 divided by 5, okay, which gives us the square root of 5.383, which is equal to 2.320. Okay, so that's our first way of computing the sample standard deviation. Now, the second way that we can compute the sample standard deviation is using the computing formula. So the computing formula says that the sample standard deviation is equal to the sum from I equals 1 to n of xi squared minus the sum from I equals 1 to n of xi all squared divided by n minus 1. Oh, and this part is over n. And again, this whole thing is meant to be within the square root. Okay, in order to compute this value, what we have to compute is the xi squareds, and then we have to add those all together. So we already know that the sum of xi is equal to 71.1 because we computed this when we computed the sample mean above. So we have already shown that the sum from I equals 1 to 6 of xi is equal to 71.1. All right, so what is the sum from I equals 1 to 6 of xi squared? Well, this is going to be 8.3 squared plus 10.5 squared plus 11.1 squared plus 12.9 squared plus 13.8 squared plus 14.5 squared. Okay. And if you're not sure where these values are coming from, again, these are just the x1 values to x6 value we labeled above. This is the same thing as x1 squared plus x2 squared plus x3 squared plus x4 squared plus x5 squared plus x6 squared. Okay. And that gives us 869.45. Okay, so now all we have to do is plug these values into our computing formula. So we're going to have 869.45 minus 71.1 squared over 6 divided by 6 minus 1, and then we take the square root. And then we are going to have the difference between these two values. So we're going to have 869.45 minus 842.535 divided by 5. Okay. And then you'll notice now, what does this give us? This gives us the square root of 26.915 over 5. So that's the same result that we found for the defining formula, which means that we will end up with the same result. Because, again, the computing formula and the defining formula are two different ways of doing the exact same thing. So we don't have to use both of these formula when we perform our calculations. We just have to we pick one direction depending on the information given to us. In general, the computing formula is faster, and then we work through the calculation. But if we want to, we can check our results by computing it using both the defining formula and the computing formula. Now, we've talked about the definition of the mean in previous illustrations. So we know that the sample mean is simply telling us that the average girth of black cherry trees is equal to 11.85 centimeters, right? Because that's what we computed above, or 11.85 inches. Okay, so average girth of black cherry trees is 11.85 inches. All right, what is the sample standard deviation telling us? The sample standard deviation is a measure of how far the girth of the trees fall from the mean. So the interpretation of the sample standard deviation in the context of this problem would be something like this. On average, the girths of black cherry trees fall 2.302 inches. No, sorry, 2.320 inches from the mean. So essentially what it's doing is it's telling us how the values disperse from the mean. So the average distance of each observation to the mean is 2.32 inches. Okay, so this exercise was an illustration of how to compute the sample standard deviation in two different ways. Again, you only have to use one of the two formula when you're computing sample standard deviation. But since we have two formula, this is a way for you to self-check your calculations. And we also looked at another illustration of how to compute the mean, which, despite the summary notation, is the same as it was before. You just add the values together and divide by the number of values. As always, if you have any questions, please let me know.